Okay, we're recording, so we're good. All right, so at the end of class last time, we pressed our magic green run button, and we got this nice plot here. So what do we have in this plot? Does anybody remember what we were doing last time?
The derivative for the back method and center method.
Right, so we calculated, I gave you position data of some marker, and we were trying to calculate the derivative of that position data. So the derivative of position with respect to time is what quantity? Velocity. So this is a velocity that we plotted here. And we've got three different curves. And like Abdul was saying, we've got three different ways of calculating that derivative. So we calculated the derivative, using a finite difference, but there's three different ways to calculate that finite difference. We could use a forward method, we could use the backward method, and we could use the central difference method. So we've got those three methods, and if we look at the plots here, we see that they all give us slightly different answers, right? Our three curves are not on top of each other, they're all kind of offset a little bit from each other. So the type of finite difference that we use to calculate the derivative depends, kind of makes consequences for what we get as the result. If we were to like zoom in on this a little bit and look at those three curves, we see that sometimes they end up being the same values, but other times, we have quite a bit of a difference between the three values. And as we kind of calculate this for, say, we've calculated the first derivative, we calculate velocity. If we were to calculate this for the second derivative, acceleration, some of these differences would get bigger. So our differences between the forward, the backward, and the central difference are going to depend on how many derivatives that we take. Because as we take derivatives, more and more derivatives, our error values go up. And so we kind of get more and more error the higher the derivative we have. So whenever we're calculating numerical derivatives, in any sort of software package or in MATLAB or anything like that, we just kind of have to be aware that there are three different methods and they have advantages and disadvantages. So the central method tends to be the most accurate one, but what's the disadvantage of using the central method? Does anyone remember? What do we lose when we use the central method? Both ends. So we lose 2 data points. So although it is the most accurate one, we have to throw out 2 data points, and so that's kind of a disadvantage. If we use the forward or the backward difference method, we only throw out 1 data point. We either throw out the first one or the last one, but they're not as accurate. They don't give us the same, kind of the true derivative. So there's, like I said, there's advantages and disadvantages to each method. So that kind of wraps up my discussion about derivatives, and what you guys are going to do on your in-class exercise, your first problem, is to calculate, using the finite difference methods, the 3 methods that we've talked about, calculate the derivative of a known function, so of a sine function. We know what the derivative of sine is, and so we can kind of compare what our finite difference gives us versus what we actually know is the analytical or the true derivative of the sine function, and kind of see what happens to the errors with that. So that's what you guys are going to do on your in-class exercise. So today we're going to introduce and talk a little bit about numerical integration. And I don't have a whole lot to say so that you guys have a good amount of time to work on your in-class stuff. So with numerical integration, we're going to focus on this problem. It's our question of the day. So we have an 11-meter beam that's subject to some load, and we can calculate the shear force in our beam as a function of the length down the beam using this equation for our shear force. So that's a given piece of information. If we want to calculate the bending moment on the beam, does anybody remember from statics how we calculate a bending moment given a shear force? Anybody dredge that up in the back of their mind? Something? So we can use some equations, and what it boils down to is that we can take the integral of the shear force over a length of the beam, and that gives us our bending moment. So integrals are important in a lot of different engineering calculations. One of the applications of that is to kind of in statics to calculate moments and things on beams. So we're going to calculate the bending moment of our beam using this integral equation that we have. And we've been given some information, because whenever we take an integral, we always need kind of initial conditions of some sort. So we have an initial moment, or m naught, we're going to say is equal to 0. And we know that the length of our beam is 11 meters. So that's some given information that we've got. So whenever we are calculating an integral, what does that represent? If you were to tell somebody that didn't know anything about math and didn't know anything about integrals, what would you say that the integral represents? Yes, sir? The area under the curve. So I've got the nice figure there. It's a shaded area underneath the curve. So an integral, in simple terms, without understanding anything about the math, is just the area underneath that curve. So the question is, how do we calculate that numerically? How do we actually figure out what that area is and quantify it? And so how can we numerically calculate the integral? Can I just, shade that little box in MATLAB, and MATLAB will give me a magic number? It's not that simple, right? So we need some sort of formula, some sort of way to calculate what that integral is. And you guys might have talked about these things in calculus way back when, so it might have, this might dredge up some of those maybe fond memories of calculus. So can we calculate exactly what that area under the curve is, or do we need to estimate it or kind of approximate it or get it close? What do we think? Can we calculate it perfectly, or are we going to need to estimate a little bit? Estimate a little bit. So almost everything that we do in this class, we kind of have to estimate or get close to the answer, but we can't quite get a perfect answer. We're going to get something that's close enough. Just like root finding, right? We can't find the perfect root. We found something that's close enough. Kind of like with an integral. So when we're talking about numerical calculations of an integral or the area under the curve, we can get really close to getting the exact area under the curve, but we're probably not going to get it 100% perfect. We're going to be close, but not perfect. So it's somewhat of an estimation. So there are a lot of different ways that we can calculate integrals. The most simple way, or the way that you're probably most familiar with, is what's called the trapezoidal rule. And so in order to use the trapezoidal rule, we have one general equation for that, and it looks kind of like this. So what do I mean by that? So if I were to draw this little figure kind of that I have on the bottom of the slide over here, I have my x-axis and I have my y-axis, and I'm going to draw my function that I have. This is the thing I want to take the integral of. And I say that I want to take the integral over a specific set of x values. So I say that the lower bound that I want to take my integral at is what I'm going to call A, and my upper bound is what I'm going to call B. And then I want to find the area underneath that curve between A and B. So if I were to shade that in, that'd be this entire area here, right? If I use my trapezoidal rule, what I end up needing to have, I need to have this information over here, B. I need to have this information over here, A. And then I need to have the corresponding f of A and f of B values. So what do we think that those might be if I was going to draw those on my plot? They're the functions evaluated at those values, right? So this point up here, this is my f of A, and this point here, this is my f of B. And then I basically connect those two dots, and I approximate that my integral is actually the area kind of in that trapezoid, or actually as I drew it, it kind of looks like a rectangle. So it can be of any shape you want. It just kind of depends on where you put your A and your B. And so a trapezoidal rule is kind of the most simple way that we can approximate the integral. Do we think it's a very good approximation of the integral as we've drawn it right here? Not really, right? So we're missing the area, all of this area up here. We didn't include that in our integral calculations. We're leaving out a whole bunch of information. So how could we possibly improve that?
triangles?
Make triangles or make smaller intervals, right? So if we drew the same exact plot over here, see how well I can draw the same thing twice. And instead of calculating the integral over one big area, if we broke it up into a bunch of little areas, kind of sub A's and sub B's, could we calculate a more accurate interval? So if I have, let's say, A1 and A2 all the way down to some A sub n, or this is going to be my E here. Go back. A1, B1, all the way down to kind of B sub n there at the end. If I were to divide this up into a bunch of little intervals and take the integral in this one, move over, and take the integral in this division, and add up all of those over the whole span of kind of the values that I want to calculate, I'm going to get a much better integral value, right? Because I'm going to be able to divide this up into smaller and smaller sections. It's going to help me calculate the integral more closely. I'm still going to be approximating. I'm still not going to get a perfect value, but I'm going to get a lot better depending on how many divisions that I use from the initial value to the final value that I have. Does that make sense to everybody? So what do I want to do when I'm calculating my integral over smaller divisions like this? I want to take the integral in each one of these divisions, however I decide I'm going to set up my divisions, and then I want to add them all up. I want to sum them up. So what is that? And each integral is going to come from that one equation that I have there. So how might we do that in MATLAB? If I was going to write some MATLAB code to do this, I can write the equation just like this, right? That would be the integral of one little slice here. If I want to take the integral in every slice, down my whole region here, and then add them all up, what kind of MATLAB code might I want to write to repeat a for loop? So for loops we use to repeat things. So we're going to say I'm going to divide up my integral into maybe 10 regions or 50 regions or something like that, and I'm going to calculate the integral in every region. I'm going to sum them all up, and then that's going to give me my total integral, or my area under the entire curve that I have. So we're going to use a for loop to be able to do that. So now if we think about this in the context of our question of the day problem. So I'm going to go back up to our question of the day. So we want to take the integral of the shear force over a bunch of x values. So if I'm going to draw one more plot, what do I have on my x-axis of this plot? What am I going to want to take the integral of? I'm going to take the integral of that v equation. What's going to be on my x-axis? The x, right? That was an easy answer. So the x, in this case, represents the distance along the beam. And what's going to be my v, what's going to be my y value? I just said it, right? It's going to be my v, which is my shear force. So honestly, I don't remember what that looks like, so I'm just going to draw some sort of random curve. Definitely not what that looks like. But what do I want to take? What values do I want to make kind of my big A and my big B here? How do I find that information? I want to take the integral over what values? Huh? 0 and 11, because I said I wanted to take my integral from 0 to x, which I said x was 11. So I'm going to take the integral from x is equal to 0 all the way up to x is equal to 11. And I want to get the whole area under the curve between those two x values. So it's going to be up to you guys. This is what you're going to work on your in-class exercise to decide how many intervals you want to break that up into. So I would suggest more than one, but you can kind of calculate that however you decide, and write the MATLAB code to be able to calculate that integral. And if we look at our formula here, what are going to be the FA and the FB? Where are those going to come from? It's going to be 0, well, could be 0 and 11, right? But what is going to be the F value at x is equal to 0? Where are we going to get that number? The shear force equation. So we plug that into our shear force equation, and then we get that function value or the F value kind of in generic terms. So that's all all the information I'm going to give you. So I'm going to pass this stuff out, and then you guys can have all of the rest of today to work on these things. We'll kind of see where we're at the end of class, and then we might have some more time. What is it? Monday is the next time we would have actual class.